guys, welcome back. Hopefully you're all doing well. Can everyone comment their name just so I can fill in the register? I got most of you down. I'm just missing Ben, Ruben, Sally, and Tom. So if you guys are here, please post a comment. All right. So yeah, things are good.
Thank you, Finn. Cool. Sorry, everyone. Yeah, missing, who I said was Ben, Ruben, Sally, and Tom. So if you guys are here, please can you post a comment so I can click you as attending. So, yeah, goal for today really is to try and get through the rest of the content. We'll probably get close to it, but we'll need to do some more practice during tomorrow's lecture. But there isn't much left. So yeah, today we're looking at correlation and regression. Sally's watching mechanic. Oh yeah, she had that thing last time as well. Cool. Hey Sally, thanks for passing that on. Good. Okay. Yeah. First thing then is I have marked. Hey Ruben, I have marked your mechanics tests. To give you guys results back to do it kind of in privacy. I was going individually with each of you. So if you do this with you guys, so you can see what you got wrong and why you got it wrong as well. My internet seems to be a bit dodgy today, so please let me know if it cuts out. If it cuts out completely, just hit refresh and it should come back. But please let me know the second you think it's up. I'll try and keep an eye on it too, but it has been a bit up and down. So yes. So it's a type of two variable stats. And correlation regression, two separate things, but the way we calculate them is kind of the same on both types of calculator. So let's get rid of all this and we'll read it. La, da, da. Cool. So if we've got data, we're talking about two variable data, so we're plotting x against y. I'll just move this back down. We'd end up normally with some kind of scatter like graph. And our correlation is basically a measure of how closely the graph approximates a straight line. So how linear the data, how linear the relationship between the two variables is. So if you've got strong correlation, it's likely your data is, quite linear. So it's you could say it's linear relationship. You could say it's the linear association. We could put that there as a keyword as well. And the way we measure it is with this thing called the PMCC, and we use the letter R for that. So that stands for the Pearson's product moment correlation coefficient. So I think I'll probably type that. But all you need to remember is it's a number between -1 and 1 that tells you how closely your data resembles a perfect straight line, be it positive gradient or negative gradient. So that's correlation. Regression is a name for the equation of the line of best fit. It's called the least squares regression line, and the reason why is the true regression equation, the true line of best fit, is the line that minimizes the square of the distance of every point from the line. So I'm not going to get into that today, but if you guys do want to look into that a bit more, have a look at one of my videos from the week before Easter, which I did in my first year class. But yeah, the least squares regression line is the line that minimizes the sum of the distance from every data point to the line of best fit squared. But that's where it comes from. I mean, it's basically a line of best fit that describes the equation of the line that you've already found the correlation for. Cool. Okay, so there are several different types of data that we could look at the correlation of. So if your data looks like this, kind of like bang in a straight line, we say R is 1. That is perfect positive correlation. Maybe it's a bit kind of fuzzier, looks a little bit less like a line. You got some data points kind of either side of it. Still, it's still linear data, so it's got strong positive correlation. So R might be a value about 0.8. No correlation would be something like this, which is the mess of data points. So R would be close to, if not equal to 0. And then you can see as well, we've got perfect negative correlation, where still resembles a line, but one with a negative gradient, so perfect negative. And here we've got strong negative. Still slightly scattered, but linear data for sure. And I've given this a value of 0.75, just because I thought this set data was slightly less correlated than the strong positive I did up there with 0.8. So that's correlation. It's being able to identify how linear two data sets are, how linear the relationship or the association between two variables actually is. Okay, so if you find out your data is correlated, it has a strong correlation, that's the case where you can start looking at regression. You can't use regression on data that doesn't have any correlation, because a line would be terrible. I could draw a line through that data, but it'd be terrible at telling me any kind of useful predictions about the relationship between those two variables. One causes the other to increase. So there was a website you probably saw last year, which is the Spurious Correlations website. This one here, if it loads, there we go. And they're quite fun. They just kind of show you, so my favourite's always is Nicolas Cage one. So the correlation between Nicolas Cage films and drowning in swimming pools is pretty strong. It used to give you the R values on these, but it doesn't look like it's doing it anymore, which is a shame. But you can see, positive correlation, quite strong correlation as well. If we keep looking through these, so you can see ridiculous statistics. One doesn't necessarily cause the other. These things have correlation, but not causation. Divorce rate is not caused by the consumption of margarine. So yeah, that's just some examples to show you that correlation does not imply causation. Just because two things happen and they kind of happen with a similar relationship, one doesn't imply that the other has happened. Cool. Right, so linear regression. To talk about linear regression, we need to first of all identify two different variables, which I'm just going to rub out and then write up again. So we've got our data on a set of axes, x and y. We need to be careful with which axis we're actually going to be using and kind of talking about. So the variable we put on the x-axis should be our independent variable, which is sometimes called the explanatory variable. And the x variable is the important one because this is the one that causes the other one to change. Time is almost always on the x-axis because nothing causes time to change. Yeah, so whatever you put on this axis should be the cause of the other thing changing. And this is why in maths we care a lot more about what x does. X is the thing we always try and solve for. It's the thing we try and integrate, the thing we try and differentiate. X is the thing we're always looking at studying, and that's because it's the independent explanatory variable. On the y-axis, we have the dependent variable, which we sometimes call the response variable, because it responds to x. X explains y, and y responds to x. So whenever we're doing a regression equation and coming up with an equation y equals a plus bx, we need to remember it's x that is describing y and not the other way around. So because of this, you can use x to predict y, but you cannot use y to predict x because y wasn't part of the equation we made up. We made up the equation based on what x was doing and how it was affecting y. It won't work the other way around. So if I came up with this line equation here, I could use any x value to predict a y value. Any x value, predict a y value, and that'd be okay. I'm not allowed to take a y value and go back to an x value. It won't be predicted accurately. Even though it looks like it would be on the graph, you couldn't trust this x value because the line is made up of x predicting y. So you got to be careful. So mathematically, we would say the line y on x can only be used to predict y values for given x values, not the other way around. If you wanted to do it the other way around, you'd have to recalculate your line of best fit using your variables in the wrong places, and then you'd be allowed to do some predictions. But it again wouldn't make much sense because usually there's a clear explanatory and response variable. So that's one thing we've got to be careful of. You can only predict. Go back to that last picture. And let's just put in some random data. So let's say this goes up to 100, down to 30. And we come up with this line. So the green line was created using the blue data. It would be safe to predict any value inside those data points. But if I tried to predict what was going to go on for x up here, maybe x is 200, I'm guessing that the line is still going to do the same stuff after those data points. So again, this kind of fits in with what's going on in the world at the moment with coronavirus. We know how things are spreading at the moment and how they have spread historically. So if I get rid of this, draw a little exponential. Let's say this is the data up to today. We don't know what's going to happen next week. We couldn't use this model to predict what's going to happen here or here because we don't know. Maybe it's going to go up more. Maybe it's going to go plateau. Hopefully it's going to drop back off. But you can't predict outside of the range of the data that you have. So if you predict inside the data, that's okay. That's called interpolation. And that's predicting values that lie within the range of values used to generate the regression equation. And that's quite reliable. Alternatively, extrapolation is when you predict values outside the range of values used to create the equation, and that's unreliable because you're kind of gambling that the trend in the data is going to continue as it has done already. And you can never do that safely. We don't know what the data is going to do after the values we've got. Anything outside that would be a guess. And the further outside you get from that, the more likely it is to be wrong. So you've got to be a bit careful when you're calculating things using the regression equation. Right, so that's all stuff that you should hopefully remember from last year. This year there is a bit of an add-on. So we have to be able to calculate the product moment correlation coefficient and the regression equation ourselves using our calculators, and then we have to be able to do hypothesis tests based on the correlation coefficient. Right, that was pretty fast. So please ask questions if you're finding that difficult, guys. But we are going to try a few questions. So if you get your I think we need calculators for this. Yeah, if you guys get your calculators out, and I'm going to show you how we can do some of these questions. I'm just going to delete these because these didn't work earlier when I did them. So if you guys get calculators out, and then we're going to try and do some of these questions. So let's bring this down a bit. So we've got the data for Camborne in May 2015. There it is. First bit, part A, state the meaning of TR. So I'm going to give you guys 1 minute to try and remember what TR actually means. So what does TR mean in the large data set? If you guys could type it in the comment section. Yeah, well, that's right. What does it relate to though? What does trace actually mean? Cool. All right. So yeah, TR stands for trace, as you guys said. It doesn't mean approximately 0. It literally means it's less than 0.05 millimeters. So yeah, that's what it means. Calculate the product moment correlation coefficient. Okay, so how we do this then? If you bring up your calculators. Oh, I'm pushing the wrong button. There we go. I'll show you this on the graphical. I've left my class whiz in the garage because I was building a climbing wall. So I'm not going to be able to do it on the class whiz today, but I'll try and do it on that one in my lecture on Thursday. So if you do want to see, it's the same method really though. You're just typing in data. So if you clear out your stats mode, if you are on the class whiz, you want to go to, I think it's two variable analysis, and then you want to go to y equals a plus bx on the class whiz, but comment if you get stuck at what to do. So we're going to type our data in. We always try and use list 1 as x. So I've typed that in with me, 2.2. For TR, we're going to use 0 because, as Ollie said, trace is approximately 0. So 2.2, 0, 1.4, 4.4, nope, not 44, 4.4, 0 again, 0.2, 0.6. And then try and fill in list 2. So 5.2, 7.7, 5.6, 0.3, 5.1, 0.1, and 8.9. Cool. Right, when all that's typed in, we first need to tell the calculator that we're now using x and y. We're using two different variables. So we need to go to calc and then set for setup. So you go to setup, you want it to read off like this. You want it to say my x list is list 1 and my y list is list 2. So we're going to type in both of those values so the calculator knows we've got x in one column, y in the other column. Then when you've done that, we're going to go to regression, which is reg. There's a load of different types of regression. All we care about is linear regression. So we're going to go for x because we were talking about y equals x. And you've got two choices. These are kind of the same thing. We're always going to go for a plus bx though, because we want b to be our gradient. So cool. So then it will do some calculations for you, and it will come up with a, b, and r. So all we really care about, because it's asking us to find the product moment correlation coefficient, is the r value. So if we just copy that off the calculator, r equals minus 0.47. Which is like weak positive correlation, so it's probably not the best data for a line. It does say as well here, state clearly how you dealt with entries marked TR. So we said TR is about equal to 0. So we used it as a 0 in our table because it was roughly approximate to 0 anyway. Cool. Okay, and then part C. So with reference to the answer you just found, what's the suitability of a linear regression model? So it's probably not suitable, weak correlation. A linear model wouldn't be very accurate. Cool. Right, while we're here though, I know a linear model wouldn't be very accurate, as I've just said. We're going to find one anyway, just because it's all on this screen on the calculator. So the model is here, y equals a plus bx, and a and b are up here. So if I want to write down my model, I can just copy it down. Y equals a, which is 5.95, plus b, which is minus 0.99, x. Just get rid of the extra plus that we don't need there. So that would be my model as kind of read off the calculator there. So if it was better correlated, if it wasn't weak positive, if it was strong positive, that'd be how you work out what your linear model, your best fit equation is for your two variables. And then we could use that to predict things or check other things. Tom, how come you're so late? I have to put you as late, I'm afraid. But if you could rewatch the beginning of the video, that'd be good. Right, anyone got any questions about what we've done so far? Nope. All right. Okay, so you guys are going to try one of these. This is slightly different. I would say they do most of the hard bits for you, but I'd like you guys to try this. It's more of a kind of log to linear form question, like you saw last year. Cool. Right, just give it a go. It's worth 4 marks. I'll give you guys 4 minutes to do it. But yeah, the trick here is log to linear form because they've done the correlation and the regression for you. You're just trying to turn their line into an exponential or vice versa. So 4 minutes, give it a go. Comment if you need any help. Yeah, looks good, Dolly. That rings a bell. All right, yeah, so we're going to try and work these out. Cool. So they've told us the data has been coded. So first of all, let's change our equation into one that kind of fits with the coding. So we're going to take this equation here and log both sides of it. So we get log d equals log ab to the power t. Then we're going to log the right-hand side, or use log rules on the right-hand side. So log d equals log a plus log b to the power t. Then we're going to use the power rule to bring the t down. So get log d is log a plus t log b, which is now in the form of a straight line. So if we compare that to the line they have up here in red, well, they already told us that x was t, so I'm going to tweak my equation here. So x is t, and y is log d. So we're going to get y equals log a plus x log b. And I can use this to find out a and b. So log b, if we look, is the thing being multiplied by x. If we look up here, the thing being multiplied by x is this, 0.0334. So I can say log b equals 0.0334. And over here, we can see the number on its own, log a, is going to be equal to minus 0.635. So that bit is this bit, and this bit without the x is this bit without the x. Cool. So in order to solve these, log without anything written here means log base 10. So I'm going to do 10 to the power of this equals b, and 10 to the power of this equals a. So if you do that on your calculator, you should get b. Oh, I've lost it. B is 1.08, as Oliver said, and A is point. Nope, lost that as well. Yep, and A is 0.232. Cool. Okay, last bit. Explain why the model is not reliable for estimating things when the temperature is 151. Well, if we look at the data so far, it goes from 38 to 94. Cool. But our value here, 151, is way outside of that range. So we'll say, it's the idea before, it's going to be extrapolation. So 151 is outside the range of data. Therefore, unreliable. And we can throw in that keyword extrapolation. Cool. Right, hopefully you guys found that okay. You're going to try one now where you have to work out the line equation, the PMCC, and do some more of this log and exponential stuff. So if we move over to the next slide, let's get rid of the answers. Cool. Right, could you guys try this one? And I think I'm going to add to this. So find the regression equation. D, use it to predict the rainfall when the temperature is, let's go for two of these. We'll go for 5 degrees and 24 degrees. So when it's cold and when it's really hot. And then last bit, actually, let's make one of these a bit easier. Make one of these 17. 17. E is going to be comment on the liability of your answers to D. Cool. Right, if you guys give that a go, I'll give you, I think, 6 minutes to get all that done. And that should be all right. So 6 minutes. There you go. Yeah, that looks good, Lucas. Are they both reliable? Cool. All right, let's go through it. I saw some good discussion and good answers in the chat there, so that's decent. Okay, so first thing is to type all this into the calculator. So let's get out the way. Yeah, so delete all this. And type it all in. So 18, 16.4, 15.3, 15, 13.7, 10.2, 12, 12, 3, 13, 4.6, 32, 28, 63, 22. Mine's all ready to go, so a plus bx is there. So we get our correlation coefficient R is minus 0.83, which is strong negative. So with reference, comment on the suitability. It's strong correlation, therefore the linear model is valid. So if I write down our linear model, y equals 116.74 plus, or minus actually, minus 6.48 x. So yeah, because it's strong correlation, it's suitable for a linear regression model. So suitable as strong correlation. So there's part C done as well. There is my regression model. Use it to predict the rainfall when the temperature is 5 degrees and 17 degrees. So if we do 5 degrees first, y is 116.74 minus 6.48 times 5. And for 17 degrees, same thing but with 17. Cool. See y equals 84.34. And for the other one, y equals 6.58. Okay, comment on the reliability of your answers. Well, 17 is within the range, so 17 would be interpolation because it's inside this range of values. 5 would be outside the range because it's below the lowest, which was 10.2, so that would be extrapolation. So we can say extrapolation outside range and unreliable. For the other one, reliable, interpolation, inside range. Cool, that's it. Okay, hopefully everyone's right with that. How long have we got? Oh, we got a bit of time. Yeah, I think let's do one more of these. So last one for you guys to do, and then we'll move on to the new stuff. So this is 8 marks, so let's give you 8 minutes for this one. And comment your answers, and also comment if you need any help. So 8 minutes, and we will go through this one. Yeah, Lucas, I would check I would check yours through. Just check the numbers. You might have typed something in wrong. Did you log the right thing? All right, let's do this one. All right, so we need to fill in our data, which I think I did some of earlier. So yeah, we get 0 for log of n. Right, rather than yeah, just to be lazy, I'm gonna do this all on the calculator. So the calculator, you can actually type in the logs, it'll do it all for you. Cool. So in this one, we're gonna have 1, 2, 4, 7, 5. 4, 5, 7. Don't know why I said that. Oh, mucked that right up. Look at that. 1, 2, 4, 5, 7, 7. And here I can just be lazy and type in, I'm not typing the word log, but type in log 231, log 41, log 17, log 7, log 2. There we go. So I've kind of skipped the copying the table part, but you can see the values there. So we get a PMCC comes out as minus 0.98. So extremely strong negative correlation. With reference to B state, whether it's a good fit, yes, it is, because when we logged it, it was a perfect linear equation, and if we turn that back into like a logarithmic equation, it will fit an exponential model. So yes, so we'll say yes, it is linear for log n, therefore exponential for n. Which is interesting. I know this is decay of stuff, but with the whole coronavirus, that's an exponential equation. And if you log it, you get a perfect linear graph. So you could use that as a rather bleak example for this topic. All right. So the equation is found to be that, which agrees with what we found in our on the calculate screen. Find expression in terms of n in terms of t. So we need to go from the line equation to the exponential equation. So again, if we log everything, we're going to get log n equals log a plus t log b, like the one we did earlier. We're then going to compare it. So we get log a is going to be that, and log b will be that. So log a 2.487, log b minus 0.32, and we can use 10 to the power to find those values. So we get b is 0.46.9. Cool. Which I think you guys agree with, well, at least Lucas and Oliver. Thank you guys for joining in on the chat there. Yeah, brilliant. So that's a bit of new stuff. What we're going to look at now, though, is hypothesis testing for zero correlation. Now, any hypothesis testing we've done so far has always had the same kind of format. Every hypothesis test we do is we're going to take a sample. We're going to look at a parameter in the sample. In binomial, we looked at the probability of success in the sample. Normal distribution, we looked at the mean of the sample. And in this topic, we're going to look at the correlation of the sample. And in each case, we're trying to say, does this parameter in this sample likely reflect the same parameter in the population? So like we did probability, does the probability of winning in my sample reflect the claimed probability of success in the population? Does the mean of my sample likely represent the mean of the population? And in this one, yeah, does the PMCC, does the correlation coefficient of my sample likely match the correlation coefficient of my population? So you guys can kind of see, hopefully, how this all starts to fit together. Now we're going to be testing, does it have correlation or doesn't it? We're seeing if it has zero correlation. So when we do this, our hypotheses, we're going to have one-tail tests, which is where your null hypothesis is that rho is 0. Now, you probably don't know what rho is. Rho is, in this topic, we use rho is our R value. Similar to how when we did the normal distribution, we used mu as our mean instead of x bar, we use another Greek letter rho for our R value. So our null hypothesis is always going to be the correlation is 0. There's no correlation. So you can see that in the two-tail as well. Rho is 0. There's no correlation. Alternative hypothesis for a one-tail test could be there is correlation and it's positive, or there is correlation and it's negative. With two-tailed, it's just there is correlation or there isn't. Rho is 0. Rho is not 0. So you have to look at the working again to see. Have to look at the question again to see if it's a one-tail or two-tail test. If it's a two-tail test, you need to split the probability, the significance level up between each tail again, and do both bits kind of separately. It is quite easy though. So we're going to try this question. Just going to clear the screen from earlier. And the confusing thing about these is we have to, or the annoying thing is we have to use a table. So in the back of the textbook, also in the exam booklet, there is this table. There is this table to my right, I guess, to my left. I don't know. Mirror images are confusing. This table over here. And if we look a bit closer at this, on the top it has the significance level, several different ones there, and on the side it has the sample level. So we're going to go through this as an example. Hopefully you guys will see how I'm meant to be able to do these. So a scientist takes 30 observations. So my sample is 30. And straight away I could go to the table and look for the line that says 30. So if you look on the right, it says sample level. I'm going to go down and find the line that says 30, which is that line there. Okay, let's keep reading. She calculates the product moment correlation coefficient. So she calculates R to be minus 0.45. They believe there's no correlation. Okay, so H0 rho is 0. H1, well, we're trying to test whether it's not 0. We're not trying to test if it's greater than or less than. We're just trying to test is it 0 or isn't it. So we're going to say H1 rho is not 0. Okay, and we're using a 10% significance level. So that means it's a two-tail test. So each tail is going to be 5%. So if I look for the 5% level on my table at the top, there it is. So that's the column we're looking down. And then we want the value that's 5% level with a sample of 30, which is there, 0.3061. Now that is our critical value. So it could be plus that or it could be minus that, because we're looking for two different tails, positive correlation or negative correlation. So it's critical if R is greater than 0.3061 or R is less than minus 0.3061. In other words, it's critical if our value is more correlated than that critical value. So if we look back at the question, the R value that they found from their sample was minus 0.45. Now that is more critical than 0.3061. So we can say minus 0.45 is less than minus 0.3061. I've run out of room. No. Therefore, critical. Therefore, I'm not going to run out of room here. So therefore, it's critical. Therefore, accept H1 and the two reactants are correlated or associated, if you like. There is an association between our values. Cool. Does that make sense, everybody? So we use the sample size and the significance level to find a correlation to compare to. And if we're more correlated than this value, we reject H0 and accept H1. Cool. Right, you guys are going to try one. You're doing pretty well for time, so here's one for you guys to try. I will just stick a copy of the table. Hopefully you guys can see that all right. Got a sample of 15, so I can make this a bit bigger. There you go. Cool. Right, if you guys could give this a go. Oops. I'll give you 5 minutes to do this. So give it a try, see if you can find whether these do the hypothesis test on these variables. Cool. How do you know if it's two-tailed? Read it through, see if they're saying less than, greater than, negative, positive. See if they're saying negative or positive correlation. If they are, then you know it's one-tailed. If they're saying not correlated or correlated, you know it's a two-tailed. That looks good, Oliver. Cool. Cool. Right. So, let's write down R first of all. So R, oh, it's on big pen again. R is minus 0.43. Samples is 15. So it's this row here. Test at the 5% level. So 5% is here again. I'm assuming it's a one-tailed. Yep, negative correlation, so it's a one-tailed test. So H0 row equals 0. H1 row is less than 0. Cool. All right. So we're gonna look through. That's funny. Move my face out of the way. So we get 0.4409. So 0.4409. Remember, it's not needs to be negative for this. That is less than minus 0.43. So minus 0.43 is not critical. Just. So therefore, we accept H0. There is evidence to suggest no correlation. Between, what was it between? Solvent and reaction rate. Cool. Right, we've got 15 minutes left. Yeah, I think I planned one more of these. So if you guys could try this one. I'll drop that picture back in. Cool. Right, can you guys try this one? And then that'll be it for today. So 5 more minutes for this. Starting from now.
Right. So let's work our way through this one. So they believe there is a negative. Sorry, guys. I barely see that again. Negative correlation. So it's going to be a one-tail test. So H naught rho is equal to 0. H1 rho is less than 0. We need to work out the PMCC on our calculator, and then we're going to look at the 1% level. We've got sample there 1, 2, 3, 4, 5. So sample is of 6. We're looking at the 1% level, so we're looking for 0.8822. So that's going to be our critical. So bring up the calculator, type in all the data. Two, 93, 91, 82, 91, 100, 2500, 27. So R is minus 0.846, or it's going to be close. Okay, so we are slightly under our critical value, so we are not going to be critical, so not critical. Therefore, accept H naught. So evidence to suggest no correlation.
Sorry guys, I put the mic on my head again. Did you get all that? So worked it out. Not critical. Therefore, we accept H naught. So there's evidence to suggest no correlation between humidity and visibility. Cool. Right. Anyone got any questions? So tomorrow I'll do a bit more practice on this, and then maybe start looking at revising all of stats as a whole. Same thing for Friday stats revision. If any of you guys want your mechanics test marks back, I want me to go over it with you. I'll be doing that today, tomorrow, and Thursday after. Well, now pretty much. If you do want to do that, you can send me a message on Microsoft Teams, and then I'll give you a call at some point, either in the next hour or tomorrow or the next day, and I can quickly go over your stats tests with you. Make sure you're getting the assignments done, and you should also still all be doing past papers. Every week you need to revise just in case you need to sit the A level at some point. So if no one has any questions, I'm gonna get going. I'll wait a minute just to see if anybody does though. Nope. All right. I'll see you guys. See you guys tomorrow then. Cheers. Bye.